Hi everyone, we would like to show you the way of solving problem by using Simplex Method.
The objective function for this question is maximum z is equal to 5x1 plus 9x2 minus 7x3. There are three constraints in this question. First, x1 plus 3x2 plus 2x3 is less than or equal to 10. Second, 3x1 plus 4x2 plus 2x3 is less than and equal to 12. Third, 2x1 plus x2 plus 2x3 is less than and equal to 8. All variables are non-negative, which is greater than and equal to 0.
Convert the LP model to standard form by adding the select variable into each constraint. All variables, including select variable, are non-negative.
Next, put the standard form into the initial tableau, where the basic variables are S1, S2, and S3, and the non-basic variables are X1, X2, and X3. Since this is a maximum problem, we'll choose the most negative variable X2 as the entering variable. Then, we will calculate the ratio to find the leaving variables. The ratio of S1 is 3.3, S2 is 3, S3 is 8. S2 is chosen as the leaving variables because it has the smallest ratio. Then, we have to change the intersections between the entering variables and the leaving variables to become 1, while the others become 0. Next, we will proceed to the next tableau, which is tableau 1. The new basic variables are S1, X2, and S3. And the new non-basic variables are X1, S2, and X3. To change X2 become 1, we have to use elementary row operations, ERO. These operations is also applied to other rows to change it become 0. The ERO for row 0 is row 0 plus 9 row 2. After our calculations, we get x1 equals to 7 per 4, x2 equals to 0, x3 equals to 23 per 2, s1 equals to 0, s2 equals to 9 per 4, s3 equals to 0, and the right hand side equals to 27. The ERO for row 1 is row 1 minus 3 row 2. After our calculations, we get x1 equals to negative 5 per 4, x2 equals to 0, x3 equals to 1 per 2, s1 equals to 1, s2 equals to negative 3 per 4, s3 equals to 0, while the right hand side equals to 1. ERO for row 2 is row 2 divided by 4. After our calculations, we get x1 equals to 3 per 4, x2 equals to 1, x3 equals to 1 per 2, s1 equals to 0, s2 equals to 1 per 4, s3 equals to 0, while the right hand side equals to 3. ERO for row 3 is row 3 minus row 2. After our calculations, we get x1 equals to 5 per 4, x2 equals to 0, x3 equals to 3 per 2, s1 equals to 0, s2 equals to negative 1 per 4, s3 equals to 1, while the right hand side equals to 5.
The conclusion for this tableau is: first, all variables have non-negative coefficient in row 0. All basic variables have 0 coefficient in row 0. All non-basic variables have non-zero coefficient in row 0. Hence, tableau 1 is the optimal tableau. Thus, this LP has a unique solution. The result is x1 is equal to 0, x2 is equal to 3, x3 is equal to 0, s1 is equal to 1, s2 is equal to 0, s3 is equal to 5, and the last z is equal to 27.
Next, convert primal to dual LP. This is primal LP. This is dual LP. The number of constraints in the dual problem is equal to the number of variables in the original problems. Coefficients of the objective functions in the dual problems comes from the right-hand side of the original problem. Since the original problems is a maximum model, thus the dual is a minimum model. Since the signs of the constraints of the original problems is normal maximum, it satisfies the maximum problems, while the dual LP is a minimum problem. So it consists of normal minimum signs in each constraint. In this case, all the variables including primal and dual LP are non-negatives.
So, we will get the solution for dual LP from the optimal primal tableau. Last but not least, y1 represents the coefficient of s1 in row 0 primal, which is equal to 0. y2 represents the coefficient of s2 in row 0 primal, which is equal to 9/4. y3 represents the coefficient of s3 in row 0 primal, which is equal to 0. w represents the optimal z, which is equal to 27.